Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, hello. There is a cocktail party later. Stuart will tell you at the end the same details, so that will be useful. I'm sufficiently intrigued by the size of the audience that I'm almost tempted to get you to introduce yourselves to us first.
The other way around.
Yeah, why don't you sit up here and we'll sit down there. So the complaint one normally receives at panel sessions is, I went to a panel session and all I got was 4 people telling me some stuff they were already going to tell me. So I've asked the 4 panelists to prepare some stuff to tell you that they were already going to tell you. Why? Because you'll get some, I want them to tell you who they are first, so that you can start really grilling them about things of interest to you. We will do that by, I will first of all give you short bios of everybody, and then I'll open it out to the audience to ask what questions you may be interested in, and then they'll tell you what they were going to tell you anyway, but slightly slanted based on your feedback. So the people involved are these people in an order that I found aesthetically pleasing. And the chair is me. I got my PhD in Edinburgh in '97. I worked in Oxford University and then at Microsoft. And in the meantime, I started a company called 2D3. And what 2D3 sold was some computer vision software, which analyzes video, discovers the camera position from video, and then allows you to play back the video with candles floating in midair, which would otherwise be difficult to arrange. And that piece of software is called Buju, and we won an Emmy for it some way back. Recently, I've been more interested in the problem of analyzing video of moving objects which change their shape, and I demonstrate that I have done that by sticking a mustache and eyebrows on this young man. So I'm interested in computer vision, the vision of a 3D world, or performing vision in a 3D world, even when that world is changing shape. Jamie Shotton is a PhD graduate from Cambridge who worked for a year at Toshiba before joining us in Microsoft. Some highlights are, my favorite items of Jamie's research are, in his PhD work and around then, he went back to look at a cue that people had looked at a long time ago for object recognition, which was the outlines of objects. It kind of seemed like the obvious thing to look at, and then it was abandoned for maybe 20 years before Jamie looked again at edges and showed that they could be used to recognize very complicated objects. So you can recognize a horse despite many changes in appearance and shape. Later, he abandoned contours, just as everyone else had, even though I thought they worked really well. Why? Because he wanted to label every single pixel in an image with what was underneath it. So this image is labeled as water, cow, grass, etc. And he was able to do that very fast. So here's a video where in real time he's labeling every pixel of every image in the video independently with one of these 20 object categories. He has applied that work to medical imaging, where obviously expert cardiologists don't need to know what part of an image is the object that they are interested in, but increasingly medical images are being viewed by non-specialist cardiologists and ultimately maybe by us ourselves. So Jamie's work can identify key organs in a medical image, something that's relatively sufficiently difficult for humans that all I can think of is this looks like a kidney. I'm sure that's wrong. And finally, Jamie has recently had a very clever transformation of the object recognition problem into the human body prose problem, a problem that people had been addressing for a very long time, and Jamie had the key insight that means that Kinect can now track your body in real time. John Wynne is another Cambridge PhD graduate who came straight from Cambridge, effectively, to work with us at Microsoft. John is an expert on machine learning, and his PhD work was on making the programming of machine learning applications much simpler. The idea is that you could draw a graphical model with the random variables that you were interested in, link them together graphically, and you would get a program. This system developed into something that I'll tell you about in a minute, but was a very interesting early effort to get machine learning into the mainstream. John applied machine learning again to the object recognition problem. Why? Because this was certainly the biggest problem around in computer vision for the last 10 or so years. John's was one of the first systems that... The key to John's research is he takes a problem, looks at it, and says, I'm never going to be able to solve it that way. The problem used to be, say yes or no, is there a car in the image? The only way I'm going to be able to solve the problem is by making it harder. So John was going to answer the question, is there a car in the image, and if so, where it is? Making the problem much bigger led him to give a much better solution than anything that was known then. He's applied this object recognition work to a variety of real-world applications, or more or less real-world applications, one of which we'll see later, which is a collaboration system, and one of which just demonstrates that we can recognize real-world objects in real time. And his most recent efforts have been devoted again to making machine learning available to the general public. The system infer.net is a probabilistic programming language, or a framework for probabilistic programming, which has been applied to medical problems, to problems in computational biology, and again is one of the tools we've used at various stages in developing Kinect. Patrick Bodiche received his PhD, I say, from Darmstadt, and I've probably got the year wrong. Have I got the year wrong?
Yeah, no, that's right.
Okay, well, it may or may not be then. Has worked at Xerox, again at the ubiquitous Microsoft Research, and is currently at the Hasse-Plattner Institute. Patrick sent me some slides for this bio, which were so much prettier than the ones I'd assembled that I had to just present them without any Chrome. I'm going to give you a very my take on Patrick's career. For me, Patrick's career is about infinitely large displays in infinitely small space. So some examples are Halo, where he indicates what's happening off the edge of your mobile phone screen by the presence of these circular arcs. Small radius arcs are nearer to the outside of the screen, and large radius arcs indicate something far away. He's been moving towards more interactive devices, and again, something I really like is the Lucid Touch system, where this finger is touching in the conventional way on the front of the screen. This finger is behind the screen and is touching the other corner of the rectangle. So here we can see a demo where we have conventional touch at the front, and then we can see the shadow, the camera's shadow of the finger behind, which gives us multi-touch in a very easy-to-use way when you're carrying something. What I found very surprising was the observation that the resolution is better for the finger behind. So a recent project, NanoTouch, again has this idea of touching the front and on the back. But what NanoTouch shows us is that much smaller devices can be enabled with this back touching, and you can be much more precise. For simple reasons, you can see the tip of the finger effectively. So this is an exciting movement, because it suggests that even tiny devices with very small screens can nevertheless be interestingly interacted with using touch. So we have a pendant shape or a watch shape form factor, or even something on a ring. He will tell you, in his recent keynote at Mobile HCI, he's been talking again about this, both the democratization of these interactions, and the idea that with a computational tool of a mobile phone, in developing countries, we need to focus really on the computational tools that are available, for example, mobile phones, and sometimes think about new software rather than new hardware. He will tell you a little about, I talked about him in environments and displays very large. Conceptually, if you're in a room where every surface is display, the display is infinitely large. And his idea that gadgets or small objects can be made so small that they're not there, which is a concept I didn't believe until he explained it to me. I hope you enjoy hearing about it. Sharam Azadi had his PhD from the University of Nottingham in 2003 and has worked in a variety of places. I love the fact that we have a graduate of the Royal College of Art on this panel. And Sharam has been looking at all sorts of interesting hardware with a common theme that you'll discover as we go through. Second Light is a surface display which can display a different image on objects above the surface as is displayed on the surface. So we have two planes of interaction which would normally cause you complications because the top plane is all you can see. But as you can see, only the objects, physical objects, are illuminated on the top plane. So that's Second Light. Side Sight takes a mobile device and looks in this area around the outside of the device. And here we're demonstrating that I can rotate the image on this phone by moving my fingers around on the outside of the device. Thin Sight looks like just a multi-touch screen until you realize that it understands what types of objects are being pressed onto the screen. So it can distinguish a paintbrush, fingers, or any number of interaction devices that can allow you to intersect with the screen. And it does that by looking at the screen effectively from behind. So we have a shadowy view of the interaction elements. And it looks like he's deviated from his research in this C-Slate project, which is the collaboration system we saw earlier, where the other participants' ghostly hands are visible on top of your screen, which allows you to mediate turn taking. I say it looks like a deviation because the name doesn't end in light, but if you realize that Sharam speaks in a London accent, you'll realize this is pronounced C-Slite, which does indeed not deviate from the theme. And his most successful project to date, he told me, but this is apparently Microsoft confidential information, so I shouldn't be revealing it, is illustrated here. And I think you'll agree that this is a tremendous success of 10 weeks ago? 11 weeks ago. 11 weeks ago. Okay, so that's an introduction to who will be speaking. And very loosely speaking, this is a software summit. When I started thinking about this panel, I started thinking about software, and you'll hear something about John's ideas for machine learning or probabilistic software, sort of a framework or a foundation for software. Jamie will be telling you about the application of machine learning software in the product that we are all interested in at the moment. But I realized that software lives, what is software? It's algorithms plus data structures. Well, algorithms and data structures don't give you anything unless you put some data into the data structures. That's machine learning. And unless the algorithms have something to run on and something to feed into them. And that is the hardware of sensing and display. And again, Sharam will talk a little about the foundations for hardware, ways in which we can enable hardware tinkering, make that much simpler. And Patrick, as I say, will talk about sort of the far reaches of what hardware can mean to us. So these are the areas that we're going to cover. I would like, so now I'm basically going to say, before they give you their talks, can you ask them questions about what they're going to be? So it's time for questions. Actually, you should probably applaud, because that generally wakes people up, and then we get questions. Excellent, well done. Yeah. So does anyone have any question that they think this session might answer for them? Really, no questions?
Well, no one was. I would be really interested to learn a bit more about... Thank you very much. I would be really interested to see, most of you come from a computer science, computer engineering, whatever background. Where do you merge when you say you're working towards, moving towards natural interfaces? Where do other areas like design and what we previously saw like social science come in? And is there something what can be called natural interfaces? Because I see a lot of things that are extremely interesting, but they still seem partly also to come from a paradigm where you interact with a computer. Whereas I would never gesture or command or do anything towards my chair. I simply sit down because it's in my natural interaction. The thing is just doing, and it affords things that I like to do. But I don't deliberately do it. So I would be really interested in where you see that kind of undeliberate kind of things moving in.
So I will first claim, because I've seen all their slides, that certainly John and Patrick, I think, addressed this question quite directly. Would you agree? Do you think you'll be answering that? I'm kind of collecting them, and I'm just checking that you're confirming that you're going to talk about them to some extent. Yeah.
Hi.
I'd like to see if you could make machine learning really easy for people to use in programming. So infer.net is the start, but it still requires a PhD.
Okay, excellent. Easy machine learning, really easy machine learning. I think John will be, yeah. And if I think no one's going to do it, I'll just say.
Well, the Kinect seems like a wonderful idea, but not just for games. So I would be curious about your vision of how, for, let's say, serious stuff and the new way of interacting with people. I understand the interest for games, but beyond games, what is your vision of that kind of interaction with Kinect?
Jamie, will you be covering something?
Talk a little bit about
Right.
possibilities.
Very good. Yeah. Anyone else doing that? Jamie's your man? Okay.
Looks like it.
Okay, excellent. Thank you. That's slightly calibrated us for what the audience is doing. And now I'm going to decide the order in which the speakers will appear. I think John has some work to do, but I think it's worth Jamie sort of drilling us down on machine learning first and how it interacted with Kinect, or how it was important for Kinect, before we get John. So let's go Jamie, then John, and then I'll decide amongst the other two. You.
Okay.
Very good.
Am I on? Yes. Okay, thank you, Andrew, and good afternoon, everyone. So just very briefly, I'm going to give you an overview of some of the work we did towards Kinect, and in particular how we went about making Kinect robust. And when I say robust, here I mean that it's going to work for everyone. You don't have to go through any calibration step. You can just walk up, you can jump in and play, and also that it's not going to ever truly break down. It's never going to lose you so catastrophically that you'd have to reinitialize the thing or recalibrate that kind of thing. So I expect most of you know what Kinect is by now. It's an add-on for your Xbox. You can you plug it in, and then it's able to track your body in real time, 30 frames a second, tracking about 20 different body joints in 3D. On top of that, it also has face recognition, so you can walk up and it will log you in. It has voice recognition, so that you can control the Xbox using vocal commands. And we've seen some of the pretty magical experiences that Kinect has enabled, especially in the sphere of gaming, but also in more general home entertainment, accessing your media library, playing videos and pausing them with your voice. And crucially, you don't have to hold anything special, you don't have to wear anything special, there's no remote anymore. And this really means that anyone can just get in and play, there's no barrier to entry, you don't have to learn how to use a controller. So I'm going to talk briefly about human pose estimation, what we are trying to achieve, what makes it hard, and how we went about it for Kinect. So at its heart, the idea of human pose estimation is you take an image, such as this cartoon man here, and you're trying to find the positions of the various different joints in the body. Here I've marked them as blue crosses. And further, you want to link them up together into this nice skeleton. And wouldn't it be great if we can also do this in 3D, so we have a full 3D understanding of your body? And what this means in practice is that we're trying to estimate the X, Y, Z coordinates of each of the different joints in the body, or equivalently the angles between those joints. Now, when Kinect came along, the hardware side of Kinect at least, the main innovation that I saw out of it that really enthused me as a computer vision researcher was the depth images that it gave us. So I'm going to play you a little video here of what a depth image looks like. And what you'll see here is that you've got the person there where the shade of gray indicates how close the person is to the camera. As you get closer, it gets darker. As you go further away, it gets lighter. And this has some wonderful properties for helping us with the human pose estimation task. In particular, you don't have to worry so much about what's in the background. The person stands out from the background really well. And you also don't have to worry about what their clothing is, what they're wearing, what the texture of the clothing is, the hair color, the skin color, all of these things that would otherwise be a nuisance to you as a computer vision researcher. A couple of things to note. As you see from the side view and top view here, it only gives you the front surface. So there's only really a single view of the person, even though it's depth. So it's not really, you could call it 2.5D if you want to think of it that way. So this really, the Xbox came to us with this camera and said, okay, we've got a prototype algorithm, but it's not robust. There are scenarios where it breaks down. Can you help us with this? And we thought, well, okay, we'll have a go, but this is a hard problem. This is something that people have been working on for 30 years or so in computer vision. And these are some of the reasons that make it hard. You've got variations in pose. The human body can get into a huge variety of positions. You've got variations in weight and in height. And you've got people wearing different clothing. And this is after you've got the depth camera. So if you didn't have the depth camera, you'd have other extra hard things, such as the color and texture of your clothing and what's in the background. So the depth camera gives you a lot of boost, but it's still only a camera. It doesn't give you an interpretation of what it's seeing. And that's what we were tasked with coming up with. And this was the result. It's called body part recognition. And it's really an intermediate step that simplifies the problem. What we really want to do is go from the image coming off the camera and produce these positions of the joints. But instead, what we decided to do was solve this intermediate problem where you try to label each pixel in the image as belonging to a number of different body parts. So for example, the left hand there will always appear orange, no matter what position the person gets their body into, and no matter what their body shape and size is or the clothing that they're wearing. That's the goal. And if we can define these, if we can find these parts and we define these parts to be spatially localized near where we're interested, the joints that we're interested in, then we can cluster those to tell us where the different parts of the body are. So some of the properties of the body part recognition algorithm, first of all, we don't use any temporal information. We look at one frame coming in off the camera at a time. And what this means is that you can never lose track. So a lot of approaches to human pose estimation use what's called tracking. And in tracking, you assume you know where the person is at this time step, and you assume that they're moving relatively slowly, so that at the next time step, you can predict where they've moved to, and then just do a little local search in the image to align your model with the image. And this works great, but it can break down when you're moving too fast or unpredictably. And so by looking at just a single frame at a time, we can avoid this problem and avoid losing track. It's also very local. So instead of trying to work out the position of the human body as a whole, we're trying to look at pixels individually and work out which part of the body those pixels belong to. If you try and look at the whole pose at once, then you have an unfortunate combinatorial explosion in the number of poses the human body can get into. For example, as for every position I can put my right arm in, I can also put my left arm in an equal number of positions. And so we get this very large growth in the number of possible things we'd have to test. Whereas if we look at just individual pixels at a time, this burden is reduced dramatically. And the other feature of this algorithm is it had to be really fast. So we were running on a set of constraints which were really that we had to run at about 10 times real time on an Xbox 360, which is now going on 6 years old hardware. And so we relied on some very, very simple depth image features that could extract salient information from the depth image, and a very simple machine learning approach called decision forests that could be evaluated efficiently on a GPU in parallel. Now, we took a machine learning approach to this. We didn't think that there was any hope of us hand-coding a body part recognition algorithm. And so we turned to machine learning, which John will talk more about a bit later. But to train a machine learning system, you need data. And in our case, because we've got such a hard problem, so many poses we need to worry about, so many different body shapes and sizes, we needed a lot of data. And there was no way we were going to be able to generate this data by recording different people doing different actions. So instead, we used synthetic training data. We used computer graphics to render images of different people in different positions. And we're going to use this synthetic data to train our machine learning system up. And we're going to, by having a massive training set, which includes variations in all of these nuisance factors down here, we're hoping that the machine learning algorithm can just work out what features to use, what's the useful information to be had from the image. Just to give you a sense of the scale of the training data, here's a little video where I show some of the images that we used to train. And I've just built up a deep zoom image here so I can keep zooming out, and you'll start to see more and more of the scale of the training data. And you'll actually see as I zoom out 1 million images here arranged so that they spell out Kinect. But I can zoom in anywhere on this image, and you'll see just the vast array of different human poses and different shapes and sizes that we use to train this thing. So just a very high-level view of what's going on inside. So we're taking this training data and using it to learn some parameters of a decision tree. So here's a little toy decision tree where the task is to decide which pixels belong to the left side of the body and which pixels belong to the right side of the body. And what we do is for each pixel in the image, we pass it into this tree, and we evaluate some feature here called F, and that just looks at local patterns of depth and the difference, say, between the depth here and the depth 10 pixels to the right. And by comparing that depth to a threshold, theta, that's learned, we can make we can glean some information about the pose. So in this toy example, we might have met this criterion about theta, and we branched down the right branch. And we reached a leaf node here where, during training, it learned a distribution over the different classes that were present. Here there's a left class and a right class. So this node might be quite confident that we are on the right side of the body rather than the left side. If we went down the other branch instead, if we hadn't met that first threshold, we would evaluate a different feature. Perhaps this time it will look upwards in the depth image, and compare that to a different learned threshold. And if we say we went left this time, we'd now be more certain about being in the left, on the left side of the body. Whereas if we had gone right, we'd still have high uncertainty about which side of the body we'd ended up on. And to train this decision tree classifier up, essentially what we're doing is we're looking for cases like this, where there's high uncertainty, and trying to find features of the image that will help reduce that uncertainty. Here's just a little graph of the scale of the training problem and why it's necessary to have such a large training set. As you can see, there's a pretty massive growth in accuracy as a function of the number of training images, although it does start to level off. Okay, so now we've got this depth image and we've gone to these body part labels here. The final step in this pipeline is to produce hypotheses about where the different parts of the joint are, the different joints in the body are. And to do that, you can think of it as sort of doing a blurring on the inferred body parts and then a clustering to make sure that you get a smooth estimate of the positions of the body. And because you have the depth image, because you have this calibrated 3D distance, you can actually produce these hypotheses in 3D. So let's have a look at what that looks like. You'll see on the top row I've got the depth image that's coming in off the Kinect camera. This is a real image now. And on the right, you've got the body parts that the algorithm is inferring at each frame independently. There's no tracking or smoothing here. And on the bottom row, I'll play it again, you'll see these joint positions that are being inferred by doing this smoothing and clustering step. And you'll see that even though there's no temporal smoothing, you're getting a really smooth signal out of this classifier that is giving a very good estimate of the human pose. Here's another example. Because the algorithm works at each pixel separately, if you've got two people in the image, it can just naturally extend. You don't have to change anything. And so as these people move around, one person disappeared behind the other. But as soon as they reappear, because there's no temporal tracking involved, then it instantly locks back onto them. And with a bit of engineering help from the Xbox team, we were able to get this to run on the Xbox 360 in about 2 milliseconds per frame, which means that the game designers still have a huge amount of processing power at their fingertips to write the game and do the graphics in the game and the artificial intelligence. Now, I haven't told you the whole story today. There's a complete, the complete pipeline has a fourth step involved, which is a bit of engineering magic on behalf of the Xbox team, which takes these 3D hypotheses that I've shown you and adds in a couple of extra constraints. It makes sure that the kinematics make sense. For example, if you've got an elbow here, you're not going to have a hand a meter that way. And it exploits the temporal information to ensure that if you, say, put your hand behind your back, it still can make a reasonable guess, even though this algorithm that I presented won't give you any information about that hand. Sorry? Okay. So that's, I think, all I'm going to talk about today until we have the panel discussion. But the messages really are that depth cameras are pretty amazing technologies. They allow us to do a whole lot of stuff that we haven't been able to do efficiently before. But they're not the whole story. For human pose estimation, there's a whole lot of different challenges that still remain even with the depth cameras. And when we were building Kinect, the main insights we had to make this robust were to treat each frame separately, to use this intermediate body parts representation that can be inferred very efficiently using fast, simple machine learning, but to train that learning system on top of a very sophisticated, massive training data set. And Kinect opens up some pretty incredible opportunities. I think there's the Kinect SDK is coming out very soon, and that's going to be really exciting. I'll just mention, in answer to your question, one application that we've been looking at on top of Kinect that's non-gaming, which is a medical application. So the idea here is that a surgeon in an operating theatre will want to interact with your data, your medical records on the screen. And if they have to touch a mouse or keyboard, then they run the risk of contaminating their fingers with non-sterile keyboards or mice. So if we can instead use gestures and no-touch interfaces to interact with the data, you can hopefully improve their efficiency and allow them to do a lot more without all these encumberments. Anyway, I'm going to stop there, and I'm sure there'll be time for some more questions later on. Thank you.
So as I think of Jamie's and John's as a sort of a two-part presentation. So I'll actually ask for questions after John's on both of them, if that's okay, unless anyone has anything particular technical about Jamie's talk that they want to ask. No, okay. So John will now give us the second half, and then hopefully between them we'll consider some of earlier questions answered.
Okay, so they told me that I'd be a machine learning person on a panel with two hardware guys showing off fantastic, cool pieces of hardware, and Jamie showing off Kinect and some amazing videos. And I've basically got to offer is statistics. So the one thing that you'll be perhaps relieved to hear is there are no equations in this talk. But what I want to hopefully get across to you is that machine learning is an enabling technology that will really help us to make user interfaces and user experiences much more natural. So why do we need machine learning for NUI? In the days of the mouse and the keyboard, the input data that you got from the device was the user action. It was a click or it was a key press. That's the action. But in the case of natural user input, the inputs that you get are these very highly structured, high-dimensional, highly complex inputs like audio, like images, like depth. And the actions that you want to get out look nothing like these signals. You want to get things like, did the user say the word start? Did they wave their hand, jump? Did they swing a golf club? And so, as you've seen in Jamie's talk, the relationship between the input and the actions is now very, very complex, and ideally something that we don't want to have to actually know much about, but we want to be able to have the machine do it for us. But there's another aspect of naturally interacting with computers, which perhaps touches more on the sort of social questions a little bit, which is that user actions are not user intent. And so even in a sort of simple case where you have someone who wants to use their Xbox maybe to do some yoga, that's their intent, but in fact they'll have to do a long sequence of actions potentially to fulfill that intent. And the better that we can infer their intent from the actions, the more happy we can make them, and the more they won't have to do any unusual actions that they wouldn't ordinarily have to do. So I'll be looking a little bit more actually about this side of things, as Jamie's already done a great job of covering an example of machine learning in the first case. So for machine learning, what do we need? We need lots of data. And so if we have some inputs here, maybe a series of images or some speech, and then the idea is that we'll get some labels for that. So we'll say, this is the image or the speech for these actions. And then maybe we'll also ask people to label the intents, what they were actually trying to achieve. And so we can get this kind of data set in which we want to do our machine learning. And so if we want to be able to map from the input data automatically to actions and from actions to intent, then what do? Is we can use a machine learning approach. We get some data like this, and then we put in, well, everyone knows how machine learning works. It's a magic black box that you put data into, and it just learns the relationship from one thing to the other thing. And so in the future, all I need to do is plug in these actions, and I'll get this intent. And so we don't use the phrase magic black box, we use the phrase classifier, but they're basically interchangeable. So how does it work? A classifier is a standard component. You pick it up off the shelf and you plug it in. And so all it can possibly do is give you similar outputs for similar inputs, for some very simple definition of similar. And so what you find is that if you want to build an application like Jamie's, you need training examples that look similar to every plausible input. And so that's why in the case of Kinect, you have like 1 million training examples. So we can solve this problem by using simple classifiers and massive data sets. The problem is there are lots of problems that are so big that we can't do this. And by using a depth camera, we can just about bring it into the space where we can. But if we wanted to go to, say, natural cameras, or multiple cameras, or more complex situations, we're going to be pushing the boundaries of what we can achieve. So let me give you an example of this. So we're going to be making a tennis game, and we want to infer some intents from the user based on some actions that we see. So we're going to gather some data from users, and we're going to get them to do some actions and say, what was your intent? So I'm going to be demonstrating these actions for you. So first of all, my intent is I want to play a topspin forehand. I'm left-handed, so I'm going to move to the left, and I'm going to play a topspin forehand. So I'm moving to the left, my arm is going back and down and then up. So that was my intent. Now here's another intent I might have had, which is just to pause the game because I've just heard the doorbell. So in which case, in the Xbox Kinect, you have a special gesture for this, which is you stand still and you move your arm out and to the left, and then you stay still. Okay? And then I'm playing a tennis game, I'm getting hot. So another intent I might have would just be to pick up my water from my table down here. So I'm going to stand still, then I'm going to reach down behind me to pick up my water, and then I'm going to bring it to my mouth. So here are 3 bits of training data that we captured for 3 different intents. Now, let's suppose that's our training data, and we have a new system in a new living room, and we see the following actions. Okay, I'm going to stay still, I'm going to hit my arm back into the left, and then I'm going to bring it forward and up. Okay? So, what's my intent?
Here you go.
So, you can probably guess that my intent was to do a tennis stroke. I wasn't doing any of the other things. But let's look at what the classifier will say. If you look at this list of actions, it has 2 actions in common with each of these. So in the case of the first one, it's got the second 2 in common. In the case of the other 2, it has the first 2 in common. So the classifier won't know. Okay? Now the way we can solve this is we can go out and get more data until we happen to have enough data that it will match our situation. And in some cases we can do that. But in lots of cases we can't. And as we want to push machine learning forward to new and exciting applications, then we need to find some other way of getting past this problem. And here's the solution. The solution is us, humans. We know stuff, right? We don't need to use a black box classifier that doesn't know anything about the world. We know about all sorts of things, very obvious things. You might call them common sense. Players playing tennis tend to move towards the ball. If you run away from the ball, it impacts your score negatively. You tend not to try and hit a ball that you can't reach. Sometimes you do, but you tend not to. And other simple things. You might want to pause a game at any time, because it tends to be about something that's not in the game. If you're drinking water, you tend to bring your hand to your mouth. You might not, but you tend to. So, and all of these things, they look like rules, but they're not rules. Everyone has tend to, prefer to, usually, typically in there. They're not rules. We can't put them into a rule-based system, but they're knowledge we have about this system. And so the question is, how can I incorporate domain knowledge into my machine learning? So here's my classifier that I just got off the shelf, like a random forest classifier, and I want to inject my domain knowledge into it, and I can't. There's no input slot to put it in. The current sort of way that you do it is you try and inject your domain knowledge into the input. So by manipulating the input somehow so that it makes it more similar, you get more similar inputs, more similar outputs. So you might, rather than just putting in a list of actions, you might take some functions of the actions, which we call features, to try and make things that have similar intent look more similar. The problem is that as you're doing it, it's very difficult to do this in a way that means that you're putting in all of the domain knowledge that you wanted to put in and nothing else. It's very, very hard to do that. So, of course, I wouldn't be telling you this if I didn't have a solution. And the solution is what we call model-based machine learning. And the idea is we replace the classifier by a model into which we can put all of our knowledge that we have about the domain. And we've been working on a machine learning system called infer.net, which you've heard a little bit about already. And all it is a system that lets you do this. It lets you build models which say something about how a system works in order to learn about it. So let's use this tennis game as an example of how to build a model. So what I want to do is say, what do I know about how someone plays tennis? Well, if they're playing a topspin forehand, what might they do? So the first thing that's going to happen is they're going to look at what's happening with the ball in the game. And they're going to say, is it coming to me or is it over to my left? If it's over to my left, I'm probably going to move left. But I might not, because everything is a little bit soft, right? So it's like a flow chart, but I have these soft arrows. So although if it's to my left, I'll normally move left, but I might not. And here's the thing. So we're going to build flowcharts of how users behave, but it's going to be a soft flowchart. Everything's going to be a little bit uncertain. And so equally, I haven't drawn all the arrows in to keep the picture simple, but if the ball wasn't to the left, I might still move left occasionally, even if I wanted to play the stroke, just because I make mistakes. Then I'm going to move my arm back. And then if I've managed to get to the ball, I'm probably going to play the stroke. If I haven't managed to get to the ball, I'll probably not do anything, or I might play the stroke anyway because I had it all set up in my head. And so, although I haven't drawn all the arrows in here, it's a soft flow chart where we're going to have dotted lines going to all of the possible actions, but I've shown the major actions in there as well. And so the thing is, we can draw a flowchart like this using all our knowledge about how people behave, but we don't really know what all the probabilities are, what the probabilities of going down all these paths are. And that's going to come from data. So this is the way we bring together the data and the model. So it's going to tell us all the relative sort of widths of all of these paths. So now I can say, what about if I wanted to pause the game? What am I going to do then? Well, I can put in another set of paths that I might take through. So I'm going to probably stay still, but I might move to the left. I'm certainly going to put my arm back and out, and then I'm most likely going to stay still, but I might do something else. And then for the final intent, drinking water, similarly, I can write a little flow chart that will take me through this system. So what this is a programming language for people. Okay? You're programming what a person does when they interact with the game. And you're writing the program of what the person does so you can understand them. So in this case, if we have a particular sequence of actions that we see, because I have a programming model for a person, I can say what is the probability that they were trying to play a topspin forehand versus trying to pause the game versus trying to get a drink of water. I can also look at the game state and I can work out whether the ball was to the left and whether the user player reached it. And from all of that, I can then do a computation that will tell me the probability of each of these intents. And what infer.net does is perform that computation for you. You just describe the flowchart it does the computation. And in this case, one would hope that it would tell you that the user wanted to play the forehand. So that was my simple message, which is using model-based machine learning, we can put the human knowledge back into machine learning by essentially writing programs that represent the behavior of people. And Infinite.net is freely available for non-commercial use, and you can download it at this address. And thanks very much for your attention.
Stay where you are for the moment. So first of all, you didn't quite answer Tony's question on how the PhD requirement is going to be reduced.
Yeah. So I think that from our experience...
I was talking to a colleague on the bus who said that they tried to use it and it was difficult.
Yes. There's two difficulties. One is conceptual, which is that programmers are used to writing programs to control a computer to do something. And these are programs that don't control the computer to do something. They're programs that describe the world so as to understand it. And that's a really big mental leap. And that one is difficult. And then there's simply technological problems like how can we make it easier to write these programs? And the way to do that is to make the tools and frameworks for writing probabilistic programs, which is what we call them, better. And we can do a lot of work on that, and we've already started doing a lot of work on that. But we're getting some encouraging signs. We have high school students who downloaded Infinite.net and have coded up programs to solve class projects. So it's not, you don't necessarily have to have a PhD. It helps. And the more we can make it look like an ordinary programming language, except that it has this completely different way of working, then the more it will be approachable to the same audience that standard programming languages are.
There's a lot coming out of that I would like to explore anyway, but again, let me know if there are other questions. Yes, please.
I'm really intrigued what you're doing because, thank you. You're really coming towards how users behave here. Where do you see that the complexity is getting too big for this kind of way of programming to handle? Because you said it's a conceptual modeling, but so if you leave so as soon as you start saying like we have certain gestures, then you still have an idea of what could go on. But what if you don't have that model anymore and you really go to natural interaction with the world? So when does it kind of collapse?
I think in the immediate future, the kind of models that we're talking about is describing the user's behavior in a limited domain. Because if you want to build a program to represent all possible behaviors of a user as they go through their entire life, you'll have solved AI. You'll be there. So for the foreseeable future, it's going to be limited domains. But maybe I can build a model to describe how someone interacts with a kitchen. Is that for 90% of activities that go on, or for 99% of activities? I don't know. This is a new language that we're really only just playing with. So I think there's some hope because user behaviors in particular locations or doing particular sets of tasks, the context can cut that down a lot. We're still a long way off from being able to cope with any possible user behavior. That's still definitely on the horizon. But I think this sort of tool will help us to get a long way towards modeling the user behaviors in a lot of domains to try and cut down the sorts of barriers that we have at the moment.
Really interesting.
I would actually like to ask the other panel members if they have any ideas on how machine learning will become easier to use. The answer may be no.
No, it is a good question. I haven't played around with Infer.net, so I don't know how easy the programming model is, but it sounds like it's accessible to people with PhDs, at least.
Or who have not yet left school.
Yes.
And as we all know, those are the two people who can actually do stuff.
Yeah.
Except for the PhDs. You guys, any feelings on making machine learning easier?
I guess maybe John can expand on this, but some of your earlier work, John, on the Vibes had, this graphical representation of the program. So you can actually, express this model literally as a flowchart as you drew it, and then you don't have to worry about being an actual programmer.
Yeah, that's a really great point. So one of the reasons we've been focusing on textual languages is because we've just been following what happened in ordinary programming languages, which is that people often there have been several sort of attempts to try and make these easy to program, make them graphical. And they tended to work for small programs, but then once the program goes above a certain level of complexity, sort of overloads your visual cortex and you can't track all the visuals anymore. That said, Infer.net programs are normally about 10 or 20 lines of code at the moment, because they usually take the form of these simple flowchart-like behaviors. And so I think that for the types of models that we can work with at the moment, graphical approaches have a lot of promise for making things easier, and that's a really good point.
I was actually just thinking, I think one of the really cool things in HCI that people appreciated was in 2004, Luis van Aert published a paper called Games with a Purpose, and I'm sure everyone, has. For those who haven't seen that, there's a game online called the ESP game. It pairs you up with someone else over a distance, and you're both shown the same photograph, and your goal is to guess, well, ESP suggests that you're having this invisible connection, but the only connection we really have is the fact that you look in the same picture, and so you're hacking in words describing that picture, and when you get it right, meaning when you have the same word the other person's ended, you get a point and you move on. So this has been kind of wildly successful, I think, to generate machine learning training data. And so, I don't know, just knee-jerk reaction. Do you think you could have a game with a purpose where people just describe everyday activities, like how they go shopping or something, and if two people kind of have the same shopping thing?
I think I exactly think that's how we should do it. So I have a vision which is kind of like trying to, so there's been databases of facts which people have been trying to put together in the logic world, where they try and gather millions of sort of common sense facts, like psych. And the problem with that is that it's in a logic world, so it's very, very difficult to be consistent, and it's very difficult to make those logical facts work for you, because you can't sort of say, make these facts consistent with data, right? But if we had more like a community effort of putting together the kind of domain knowledge that I had in my slides, but for the whole world, right? But soft. So you could say, typically, people going into a supermarket buy the fruit first or something, right? Then add in a whole load of data of video camera feeds of people going to supermarkets and make sure the two are consistent. And so I think that is what we can add to the previous psych approaches, which is we can say, here's a pile of data, here's a pile of human soft rules, make sure they're consistent, throw out the data that's inconsistent, throw out the rules that are inconsistent, and what you're left with should be top quality.
John's rule for successful operating system construction, but soft. What light through yonder windows. Okay, so we are going to finish at 5:30 because that's what we're going to do, which means these two chaps have somewhat truncated.
Yeah, we have very
because
little
I only
time.
allowed them 10 minutes. I only allowed them 10 minutes per talk, and there's 30 minutes left. So.
So we're going to go quickly. Yes, absolutely. Hi everyone. My name's Sharam Azadi. I'm going to just switch to my slides, hopefully. In the interests of going quickly, as Andrew said. Let's see. There we are. Okay, I'm Sharam Azadi. I'm from Microsoft Research Cambridge as well. From my name, you're probably a little confused as to where I originate from. That's another conversation. You're more than welcome to ask me after this panel session. At the cocktail party. Yeah, it's an icebreaker. That's wonderful. Thank you. So I'm a researcher in the Sensors and Devices group in Microsoft Cambridge. And I'm a hardware guy, so a hardware guy at the Software Summit. So I'm really passionate about hardware and the difference that hardware can make. And the ethos of our group is about taking the starting point, novel hardware, and then building on top of that, all the way up to the user experience, to deliver something that's radically new and novel. So to really understand what we're trying to achieve, here's a user interface that some of you probably aren't familiar with. This is Windows 2. Anyone remember this?
Who's used Windows 2?
People have used Windows 2. Wow. So I was a 3.1.1 man, so it predates my time. So this actually looks really archaic and old. But is it really that fundamentally different to user interfaces of today? Well, there's a mouse pointer, there's a button, there's a window, and there's a menu. So fundamentally, the paradigms in which we interact with computers using windows, icons, menus, and pointers, or WIMP, hasn't fundamentally changed for over 20, 30 years. So my argument is that the hardware hasn't radically changed. If you actually look at computing hardware, you see that the differences aren't that great. So this, anyone recognize this? This is, Patrick does.
I'm dating myself. I did an internship at Siemens, and they had a relabeled star, so I actually worked with one.
Oh, wow, wow. So that's a Xerox star, actually built by Alan Kay and other researchers at Xerox PARC. And this dates back to 1978. This gave back, life to the WIMP-based graphical user interface. But what we fundamentally see is not that much of a difference between that device and the desktop computers of the modern day. So they all have keyboards, they all have mice, and they all have a display. And that hasn't fundamentally changed for 30 years since the Xerox star was first introduced. And so our real remit is to try and change the hardware radically to really try and impact the user interface. And I'm going to give you some examples of that. The first is around Surface computing. How many of you, just a show of hands, have heard of Surface, Microsoft Surface? So this was when I joined Microsoft in 2005, this was a radical departure from what was happening before. The iPhone hadn't come out. Not many people had heard about multi-touch. And the real remit for this project was, how do we redesign the computer? If we were to throw away the keyboard, the mouse, and even the vertical display, what would a computer look like? Something that could afford more natural interactions. So the manifestation of that was something rather clunky in some senses. It was a big box with a display embedded inside it. So no longer were you actually putting a computer on top of your desk, but you were actually interacting with your desk. It was a tabletop computing device. So since then, with the rise of multi-touch, a lot of people have seen other touch technologies, and actually natural user interfaces have become synonymous with touch. But the Surface computer had a number of properties that were very unique. It actually was a fully functional computer vision system, so there was cameras inside and a projector inside that actually could see interactions on top of the Surface that went way beyond touch. I'm just going to show you a very quick example of a very early demo, back then it was called the play table. So what's happening here is we're putting pieces of objects, game pieces, onto the play table surface, and then we're remotely controlling the tank on top of the surface. Now what's really clever is the Surface computer is detecting that these objects are on top of the surface. It's also sending signals, infrared signals, back up to the tank to remotely control it. So not only can the player control the tank and shoot the virtual objects here, the computer can now control its own tank and chase after the user here. So it was radically different to what had come before it, and that's primarily because of the hardware. So one of the projects that we started to work on once we started to explore surface computing was FinSight. So this was really about taking the Microsoft Surface, which is this big clunky box, and trying to make it thinner. So a thinner form factor so that it's more appealing and more widely adoptable. So to really understand what the sort of technical research problem was, if you look inside the box, what you find is on the optics side of things, the display is a projection-based display. There's a diffuser, there's a projector inside, and there's 4 cameras that are looking up at the screen. So inherent in that, in the Surface computer, is this size, this inherent size, because of this large optical path that you require from the projector and the cameras, such that they can see the screen or display onto the screen. So what we did was throw away those optical components and start from scratch. We wanted to use LCDs instead of projectors. That was the easy part. But what we really wanted to do now was throw away the camera and come up with a sensor that could give us those optical qualities, but without requiring this large optical path behind the display. And what we actually came up with was a series of IR transceivers that could be sat inside the backlight architecture of an LCD. So the real caveat here is when you open up an LCD, and we did that many, many times, what you find is a number of optical elements, but the backlight typically is edge lit. So there's actually no light source directly at the back of an LCD. It's all around the edges. And there's in fact just a white reflector that allows you to reflect the light back through the layers of the LCD. So what we were able to do was actually cut holes within the LCD backlight and put these IR transceivers in the back, both to shine infrared light through the display and look for reflections of light through the display back to the sensors. So the real caveat was that infrared light could actually travel through all of these optical elements of the LCD. So this is the hardware that we built, the first prototype, a 7x5 matrix of these IR transceivers. The emitters are at the top, the receivers at the bottom. So we put 3 of these together to form a very low resolution sensor. We cut the back off the LCD. It's interesting, so Dell actually phoned us up during the time we were taking all of these LCDs apart and asked us if we wanted to extend the warranty on any of the laptops, which we said is probably void. So this is a unit that we developed with 3 of these PCBs at the back. A larger prototype that we developed when we started to cover the full screen. So this is giving us more or less 1,000 of these sensors and emitters in the back of the display. So this is the sort of image that you get from the display. So each transceiver provides 1 pixel of information, which is the incident IR that's being reflected through the display. By interpolating that data, you get something that looks more like hands, basically, less blocky, using bicubic interpolation. So we have now a touch sensor, and you can see the sort of fidelity of the resolution of the sensing that can actually detect a lot more than just fingertips. It can detect the shapes of your hands. It can detect physical objects that are placed on top of the surface, for example, mobile phones or a remote control. And that allows us to really think about how user interfaces can be extended. So, for example, you can do the sort of typical touch-based interactions, but you can actually start to use physical objects in interactions with an LCD. So here we can actually detect the brush strokes and adapt the paint application so that we can paint with thin strokes or thick strokes. And again, this is just a passive brush. It's just reflecting infrared light through the LCD. Another very quick, nice example at the end is this. Again, this is just a sheet of acrylic that's been laser cut, but we can detect the outline of this and actually display digital graphics underneath. So for example, here's our way of selecting the different color in our paint application. So that's FinSight. So one of the things we wanted to explore beyond that, so a lot of people who've used Surface computers will have seen demos like that. We did it in a thin form factor, so that's compelling and new. But one of the things we really wanted to explore was richer, even more natural interactions. And one of the sort of pet gripes that I have of seeing people use Surface computers is this. So we are always interacting just very carefully with our index fingers. Even in this Surface commercial, it's all about just very careful fingertip interaction rather than whole hand interaction. And this gave rise to a project that we call surface physics that I'm going to very quickly cover. I'm not going to talk about the technical details. But this is about really trying to integrate more natural interactions which use our entire hands and the contours of our hands in interacting with surface computers. So here's an example of what I'm talking about. So here we have a virtual ball that we're interacting with, but we're using the full fidelity of our hands and the full fidelity of the sensor to really interact with these objects. So we can provide torque by adding a spin to the ball, or we can knock the ball just by moving our hands quickly over the object. So it's really about enabling these more natural interactions through a regular surface computer with the combination of a physics engine. So here's some more examples of that. The physics engine allows us to model dynamic objects and non-rigid objects as well. So here we can do things like tearing a virtual object, which was really interesting when we were filming this. As we were tearing this, some of the people that were shooting the video were flinching. They were worried that this object was going to come out of the screen at them. Yes. So I am going to wrap up very quickly. I just wanted to talk about some of the new work that we've been doing on input devices, which is exciting. So a lot of you probably recognize this. This is the mouse, Engelbart's mouse, made out of wood. It's got a rotary encoder on it, but fundamentally the device hasn't changed over 40 years. Engelbart really got this device right when it came to the accuracy of pointing and the lightweight interactions that it enables. It's very easy to move across an entire screen and point very accurately with it. So what we wanted to do is bring some of those affordances of the mouse to some of the affordances and the magic of multi-touch. So we tried to combine the two together. And this is some of the work that we've been doing with multi-touch mice. So I'm going to show you, I'm going to do a demo right at the end of a product that's being released in May called the Touch Mouse. But I'm going to talk about some of the more wackier concepts that never made it to through with the product team. So this one we're calling FTIR mouse. How many of you have used or seen the ARC mouse? So this kind of is influenced by that in terms of its design. So this is using quite a common technique for detecting multi-touch. It's a sheet of acrylic, and we're shining infrared light through that sheet of acrylic. What that light does is it totally internally reflects, it bounces around, and when we touch the surface, that light can scatter down, and we actually have a camera embedded into the base of the mouse that allows us to see those interactions. So I'm going to roll the video so you can see some of the touch sensing here. So as I'm touching the surface, the camera in the base of the unit is picking up that signal. And we've also got an optical sensor in there, so you can actually reposition the mouse. And this is us repurposing some surface computing applications using this mouse. So a device that's much cheaper than the Microsoft Surface that allows you to interact in ways that surface computers allow you to do. The other more wackier prototype was almost a mouseless mouse, which we call side mouse. So this is just the base that your hand rests over. There's a laser inside that shoots across the surface of the table, and there's a camera that sees when you intersect with that laser light sheet. And we can pick up that signal and actually allow us to detect multi-touch around the periphery of the mouse as you're interacting. And there's some interesting possibilities here. So you can move the mouse with the base of your hand. As you place your fingers down, you can actually detect touch points. But you can now bring in two hands. Once this device is kind of parked, you can actually start to interact with both hands simultaneously. So it's almost like you're taking a multi-touch surface with you wherever you go. So the final device that actually made it was this capacitive multi-touch sensor. So the real innovation here was we were using ink, silver oxide, to print these traces, capacitive traces, onto any flexible substrate. So we could, rather than flexing a PCB, we could actually design any compound curvature, which makes for a much more ergonomic design in terms of adding a multi-touch sensor to the mouse. I'm going to give you a very quick demo. So the mouse is going to be available in May. It's called the Microsoft Touch Mouse. The price is still TBD'd, but here's a very quick demo. So I'll just restart the application. So here you can actually, as I'm touching the screen, you can see the sensor data. So this is giving us measurements in capacitance as we're touching the surface. You can clearly identify fingers, so I'm doing a scrolling gesture here. And on top of this, we have a gesture recognizer that allows you to do some very simple gestures. So for example, here, by just moving 2 fingers up and down on the mouse, I can maximize or minimize the window, or get the window back. If I move my thumb across the mouse here, in fact, it doesn't work with this window, sorry. I can go backwards and forwards. If I do 2 fingers left and right, I can dock this window to the left, or I can dock this window to the right. I can bring up some photos here. I can dock to the right, and I can go backwards and forwards, or I can zoom in, zoom out. Or with 3 fingers up, I can do an app selection, so I can switch between applications. So again, we're getting this full power of a regular mouse, which is ergonomic and pleasing to use, but also the ability to add gestures on top. So here we're just doing very simple inertial-based scrolling. And I'm going to finish up there. Thank you very much.
Thanks, Sharam. That was fantastic.
Thank you.
And again, I'll let Patrick start, and we will hopefully have 1 minute for a key question at the end.
Alrighty. Push the button. Oh, okay, cool. All right, so I apologize for typing while I was on stage, but as the panel progressed and time management changed, and I recognized your faces from earlier, I rewrote the talk. So here we go. So natural user interfaces. In my impression, like whenever I look at this, I get a lot of flashbacks from Ubicom, like kind of things from the 80s in a way. In some ways, I think there are 2 really exciting parts to natural user interfaces. One of them, and I really like the slogan, "You're the controller." It's about control. It's about intentional control. And so the difference is we basically do the things we did before, but we're doing it unencumbered with a high degree of freedom because we're using our whole bodies. And we're doing some research, and I'll show an example of this in a second. On the other hand, I think, and that I think Kinect is kind of the most significant thing that has happened in the past 20 years with respect to the subject of Ubicomp. I mean, Ubicomp had a lot of stuff to do with information processing that was integrated in everyday objects and activities, and I'll talk to that a little bit at the end of this talk. So I initially prepared like two things to show here. And I'll first start with the 30-second summary of gravity space, and I'll show you one thing that you haven't seen, which is called Imaginary Phone, which is just fresh off the mill, and I'll show you a piece of video we shot last week. So the idea of this is kind of our homage to like the 80s theme of smart rooms. You know, the fact that we're instrumenting the space, and that we're looking, we're working with gravity because everything is pushed against the surfaces. And I recognize most of you, so we're here, you saw this, we're building this large floor. And we're recognizing objects based on their contact area, based on these pressure images we get, detecting activities such as crunches and things like that. And actually, our way of dealing with this data is actually not that super disliked from certain things that happen inside of Kinect. So again, our specific take on this is to take a 2D perspective because we're dealing with occlusion better. On the other hand, as Andy was pointing out, in our group we've had a long tradition of making mobile devices, and so you guys saw the LuciTouch and the NanoTouch, which devices are manipulated from the device backside, and that was one of the key ideas to allow us to make these really, really small devices. And you saw like the concepts of how NanoTouch allows you to when technology has been miniaturized far enough to actually make devices that fit a finger ring. So let me show you where we're going as the next thing, which is kind of one step smaller than the nanotouch. So I was initially very tempted to show a piece of video of Steve Jobs on stage where he says like, "Who wants a stylus? No one wants a stylus." But then I decided not to do that, but sort of reenacting, if you will. So there's been a lot of debate about the stylus. So we used to have mobile device that consists of two pieces. There was like the device, then there was the stylus, and then people rightfully argued, we don't want to whip out the stylus. I think they kind of left the problem half solved because you still whip out the device, and so I want to debate with you if it's worth whipping out the device. And so so here's one of the prototypes we showed at WIS last time, and then I'll show you kind of the thing we showed last week. So this is one of our students, Daniel, and he's interacting with this imaginary interface. So he's wearing a camera on his chest, but instead of using a device, he's actually drawing something into midair. And so he's performing all the interaction that you would expect from a touch screen, except he has no touch screen. And so that's what this whole project is about. I mean, we're using very common computer vision technologies for that, like segmentation and the pinch recognition. And so, and this is the thing we shot on Friday. You'll see there's one thing that didn't quite work, but I thought you might get a kick out of this. So this is where to look. Okay, turn the device on. This is the one that doesn't work. And here we go. So set the alarm, unlock the phone, go back to the home screen, lock the device. And so we're kind of excited about that. We think it's kind of a cool thing. So it's kind of the next version. It's the one without the stylus and without the phone. So we think of imaginary phone as being a shortcut for mobile devices. So we're too lazy to fetch the stylus. For like certain micro interactions like those, like unlocking the thing, answering a simple dialogue, starting an application, just finding out what time it is or the weather or so. Maybe we're using a wireless headset for that. And so I think here's kind of the rationale. Out of 100% of different things we typically do, traditionally, in Palm days, we used the stylus for 100%. And then some rightfully said, like, okay, well, that's kind of a waste. We can do 90% of those with touch. And, we still can whip out the stylus if we ever want to sketch on this thing. And we fully agree. And we say, well, at the same time, out of the 80% that we can do with touch, maybe we can do like 60% of those actually without anything. And it turns out, if you look at, there's typically kind of a long tail kind of thing. The interactions are very complicated, a few of those. And then you have a lot of these micro interactions where you're just checking if you have new email or something like that. So can users do it? We actually did a series of studies. So here's the general concept. The idea is, the idea is that people actually use a touch device most of the time. The idea is, as they're doing this, they're learning how to interact with these things. So they're kind of coming up with a mental image of where stuff is. Because clearly you can't learn an imaginary interface just from looking at it, because there's nothing to see. Then it has to happen some sort of a transfer where you're like, oh, okay, whatever is on my device here, it means that on my hand. And then people need to be able to actually acquire this. So we've been goofing around with a bunch of studies. We went to the cafeteria, took people's mobile phones away, and let them recite how much they recall of their home screens where applications are. So everything that's white is correct, and everything that's black is wrong. And so what we found is that people on average got like, over 70% right of these, of the frequently used applications. So the next question is, does it transfer? So it turns out we didn't only ask this, we also asked that. So sometimes, like half of them we let them recall on the actual, on a prop of the phone, and the others we let them recall it, giving a simple mapping scheme on their hand. And it turns out, the recognition rate is not really different. This is a very small sample, I recognize that. So we think this is kind of promising. And then the last question is, can people actually acquire things here? And so the initial concept we had where people drew in midair actually doesn't do so well because there's very little things to hold on to. But as the moment we switch to the hands, people are actually very accurate in reciting things to their hands. So you can see the targets, and then these oval contain where they come from. The reason why it's so accurate because the hand is full of landmarks. And what's really, really cute is if you have a mobile device that has 4 columns and you happen to have 4 fingers, then that makes it for a really nice mapping between the two. So the main idea here is we think of NUI in that space kind of as the next step in mobile. So in 1996, when I had my Palm Pilot, I used this mobile device and a stylus. Then in this case, I think the iPhone has some cred in pioneering the kind of device plus finger. And so we're thinking if natural user interfaces can be the next step of like getting rid of stuff in the interaction basically, but still being kind of maintaining the spirit of mobile. And yeah, we'd love to do this on Windows 7 actually. Telecom was kind enough to give us a bunch of phones with phone plans, so hint, hint. Anyways, so here's some additional thoughts on the whole topic, which I initially thought would be great for kicking off the panel. So I think the world is really changing. When I think of like the first day I kind of saw, well, it was a couple of years ago, I saw Andy Wilson goofing around with these depth cameras, and I kind of thought of motion capture. So motion capture is actually something that's been a really, really kind of big business, but not for people like us, right? It's for people like who make big movies. Also for people who make, you know, big games. You know, people jump around in these motion capture suits, and you know, they're performing all these, you know, this training. If you buy a karate game today, it looks really natural because someone who actually knows karate kind of showed how to do that. And so, you know, he actually have this. He explains he's a really serious actor. He's doing this, you know. Anyways. So it turns out that these motion capture things are like $1 million installation. I mean, for a bunch of cameras, Vicon will take about 200,000 from you. And if you look at the whole studio, this is a really big production. And so I think one of the things that get me excited about the whole Kinect business, that I think this is one of these things where kind of some sort of crazy Moore's law is hitting us right now. Where, like, you know, a bunch of kids in the basement with $150 can effectively do motion capture, right? So it's one of these things where, like, something that used to be really only available to a few, and now becomes available to a lot of people. And so this is a video actually that I stole from Andy Wilson and Herborg Benko, who showed this at WIST. So they're, you know, let's instrument a room and make all the surfaces interactive and stuff like that. So I thought this was really cool. And I had to read the paper twice to kind of get the idea of, you know, where this is leading and why this is so meaningful, because it really means, you know, that unlike traditional mocap, I can have this at home. So my home can be a smart home now, and I can actually have these invisible mobile things and stuff like that. So, and I thought this was a great way of kicking off the panel, but maybe it's a great way of finishing the panel. I think for 20 years, the whole Ubicom community, we've all thought like, oh gosh, all these things we can do when we have indoor tracking. So let's work on getting indoor tracking working. Well, indoor tracking, here it is. So what now? And I thought, you know, maybe this is a good point for going back to the origins and kind of, you know, reading up on Mark Weiser and folks, and, you know, the whole idea of comm computing and the idea of, you know, how great the world could be if the PC was not something that's so in your face. And yeah, and essentially, you know, I think the term comm computing is probably the best summary of this. So that was my summary. Thank you so much.
Fabulous. Go. Oh, sorry, what time is it?
As there is no time, I want to ask a quick question. I think one of the things we see with natural user interfaces, and especially with what Patrick had at the moment, we make user interfaces invisible. And I think in the Ubicom community, we have done this unsuccessfully for 20 years. I myself, not for 20 years. But the idea sort of a good user interface, if you look at basically a usual textbook, you will find that visibility is a key. So seeing what people do, and I have seen this myself. So for example, with the touch mice of other companies, you have a lot of gestures, and we looked around of people using them intensely, and what you will find, nobody knows the gestures because they are not visible. We have looked into sort of speech recognition in the car. People don't use it because they don't remember what to say. And I think sort of we start now sort of, I think that the Kinect with the games, you have a lot of visibility, but the other things you were talking about, so they go into a direction where you don't see your user interface options, and I think that the nice things with menus, etc., people will remember. And okay, going sort of to clever students in a cafeteria may give you sort of some sample of the population, but I think the population is sort of much broader. And the question is sort of, by moving those interfaces away and sort of making them invisible, do we sort of create again sort of user interfaces that are really, really hard to use?
So, sorry, let me just say one thing first. We're at 5:30. If you had plans, you know, feel free to walk out. But we're happy to stay here until cocktail party time, which is apparently 6 o'clock, as this will tell us. So please go on.
So oh, am I? Turn my stuff off. 1, 2, 3, 4. 1, 2, 3, 4. Can you hear me? Okay, I'll just talk very loudly.
Patrick.
Okay, here it is. I'm like, I think Albert, you're bringing up a really good point. I think I think we had similar issues to a certain extent. I mean, the whole NUI discussion that started with Surface was kind of a similar thing, where if you think about desktop computing, you typically have a menu first, and then shortcuts come later. shortcuts are for those, you know, who don't need the training wheels anymore. And I'm one of the 5 people in the world who've really, really deeply embraced the Alt shortcuts on Windows. I don't know, does anyone else know how to use shortcuts starting with the Alt key on Windows?
Yeah, of course.
That's awesome, because it turns out you can really do everything, and that's one of the reasons why my desktop machine is still a Windows XP machine, actually, in that case. But so I think with natural user interfaces, we've kind of taken 2 steps at once to a certain extent. We try to because we didn't want any visible UI elements already on touch, we kind of skipped that point. And I don't know, I'm not sure where this is going. I would be very happy to see if we took 1 step backwards and thought about visible controls and these things. And on touch systems, it would be very easy to do. On these motion capture-based systems, it will be very hard to do. And we need to think about, maybe props will play a role, maybe tangible components will start playing a role. Maybe you will start picking up random objects in your environment and do stuff to them, and that will be the symbol.
Yeah, I think it's a really good point that you raise, Albrecht. I think one of the issues is how, in a world of invisible computing, when are you engaging with the computer and when you're not? So, you know, the example that Patrick's giving of picking up a bottle of water and it's accidentally providing input to some computing system is a difficult one to know when you're always engaging, when you're always being sensed.
Yeah, perhaps one point to follow up. We had sort of a weight sensing floor some time back, and so basically whatever you did in the room was not on a resolution at what Patrick does at the moment, but sort of whatever you did sort of changed something in the room. And to get something more than sort of the tracking out to really make applications useful is extremely hard, because sort of the idea, if you look at the use of a traditional mouse, people will lift it up very often, sort of this clutch mechanism. So how do I do that if I'm in a floor, sort of to reorient, or to sort of, how do I clutch? Basically, how do I sort of disengage myself from the control? And I think we probably need to sort of, as you said, the step back to have the visibility of what our actions are. And I think that's the question, sort of, can we visualize that something is happening at that moment, or is it sort of more the motor memory we have to tap into?
Just commenting on this, I think in many ways we were very lucky for like 41 years, which is, I think the mouse, for example, had both, it was a great input device, and is a great input device, and had the affordance that went with it, right? And so I think for a lot of stuff that we've been using, we kind of had this thing that the technology that we were kind of blessed with the fact that the technology was clunky enough that it happened to, as a side effect, produce great affordance. And, you know, whether those that didn't have great affordance, right? There was a light pen that was kind of gave you a stiff arm after a while, and, you know, people try to use joysticks in Gem or something, you know, like, you know, in certain window managers and stuff like that, and they disappeared, right? But, I mean, a couple of things were left where the technology was clunky enough. And so, unfortunately, we're kind of in the situation right now where, like, being small is really, really desirable somehow, right? And I think at some point, like, you know, there will be a battle somehow between those people who, I mean, for example, like, I don't know, I used to type on a Sinclair's ZX81, I had this foil keyboard, and I see some people my age nodding. Yeah, Sharam's nodding too. But I think that we're going to have some of these issues where, like, sometimes now we see people who design keyboards like that, right? And they don't have any keys on them anymore, and so there will be a battle somehow between, like, technical love for technology and sexiness of the UI and actually usability. I don't know. We have to find out.
Behind.
Suppose you have a hardware which is 2 orders of magnitude faster and as many memory that you wish, or what other devices. Will it fundamentally change the user interface, or you expect that it will be more of the same?
So maybe Jamie and John are people to talk about that a little.
So, I mean, in the case of Kinect, we certainly could do a little bit more if we had better, if the camera resolution was higher, if we had a little bit more processing power, we'd approach the problem very differently. And that may enable a few more, you know, qualitatively better experiences. For example, you know, if you're trying to do sign language recognition, it'd be useful to be able to track the hands in detail. And so, you know, I expect that kind of thing will happen you know, eventually as new hardware comes along. John, do you have anything to add?
I mean, from a machine learning perspective, the only thing that would make a difference is if we had an infinitely fast computer, because if it was infinitely fast, we could explore all the possible things that could have caused some data, and that's the main problem in machine learning, and then we could just go to crazy things. But until it's infinitely fast, merely incredibly fast isn't enough. So, no, it's got to be infinitely fast. So, without that, from my experience, when we found a machine learning solution to something that was slow, there's always been an engineering way of making it fast. And so I don't think that it's the performance, you know, the hardware performance that's the limiting factor. I think it's the smartness of the algorithms at the moment.
But maybe 20 orders of magnitude would be okay. That might change things.
That's 20 variables. It's
20 extra variables.
So can I summarize it that you believe that this is the end of the new user interfaces and you reach the top and from now we will have the same old user interfaces forever?
I think my answer would be the opposite. What John is saying is that computers today are the same speed as they were in 1968 from a machine learning point of view. They've got much more memory, but we haven't. The same. We will have the same.
As far as I know, all the machines in the world will be finite at some point.
Yeah, but
okay. So who cares?
Ingenuity can do what the machine cannot. Patrick.
So we just did some brainstorming in the group, and I think to a certain extent, I mean, how we tend to summarize that in a brainstorm is we say, let's assume that tracking, like anything that happens in a room, is solved. What do you do now? And I think that's kind of where the problem lies, right? I mean, I think I think that's a good point for this starting discussion. Like, just assume you know every single thing that happens in a room, right? So what can you do now? Because, I mean, we're like to a certain extent kind of there. But, I mean, but I think the problems that have come up are kind of still like the same. It's like there's ambiguity. You know, do people know what they want? You know, I mean, these discussions have been had for like decades, right? Should people be given what they ask for or what they want? You know, can you better? The whole discussion about agent-based systems versus direct manipulation is going to resurface. You know, Patty Maas versus Ben Schneiderman, and you know, all these issues are coming basically up again, just in a new flavor somehow. But I mean, the hard underlying questions of the interaction paradigms will, I don't know, they will just be rehashed somehow. I tend to think that the main constraint we have right now is not in learning more about what's going on in a room. I think we just made a quantum leap. Now we need to digest that and find out what to do with that. That seems to be the harder problem. I mean, no, sorry. I'm thinking of something. I was at AAAI in 1998, and Deep Blue had just beaten Kasparov in chess. And so the community got together and said, like, wow, what are we going to do now? Like, you know, and somewhere I expected something crazy. I heard, like, what's the new big challenge in AI? You know, once a good human had been beaten in chess. I just lost against 1,023 bytes of Java code playing chess, but that's different. And I was really surprised. I was very negatively surprised, actually, when the community, univocally said, oh, now we need to do Go. And they're like, what? You know, because, I mean, I'm not a Go player. For me, Go looks like chess. Maybe that just is a witness of my ignorance about the great game of Go and of chess, apparently. Other people had suggested, someone suggested playing Lemmings as the next thing, which is very interesting because Lemmings is something where you have not an innumerable number of moves. It's an 80s video game where like little things fall off, you know. And so you at least have to plan, which is very interesting. That's at least another category of things. But in some ways, I think that's kind of the point where we are. Like the question is, what's the new class of question, right? And not so much.
So I'm going to interrupt because Jamie reminds me that we have a train in 0 time. So what I'm going to do is say, ask you to thank these folk.